Okay, this is going to be a vodcast on valence electrons, the octet rule, and electron dot diagrams. I'm going to go through some of the definitions of them first and then kind of do some examples on near the end and then show you a shortcut. Okay, so valence electrons are basically those electrons on the outermost layer of an atom. I guess the better definition is electrons in the atom's outermost orbitals, generally those orbitals associated with the atom's highest principal energy level. So if you take a look at sodium, and we're using Bohr diagrams, it's a better way to visualize it than the actual quantum models. So with the sodium, it's got that one electron in that third layer right there. And that one electron is going to be its valence electron. That is the electron that will really participate in bonding with other elements. Elements do not really want to give up their inner electrons. So the inner electrons, you want to think of them as like money in the bank. You don't want to spend that. And the electrons in the outermost layer, you can think of them as money in your wallet. You're more willing to spend money in your wallet than you are money in the bank. And the electrons are not, atoms are not any different. So that one electron there, that 3s1, in this case, is going to be its valence electron. It's going to have 1. Chlorine, on the other hand, on its outermost layer has got 7. 1, 2, 3, 4, 5, 6, 7. And its outermost ring. And that's coming from the electron configuration 2s2, 2p5. So we add up 5, we add up 2, I guess a total of 7. So for chlorine has 7 valence electrons and sodium has 1. And these are the electrons that participate in bonding. So this kind of leads into the next concept called the octet rule. So atoms tend to gain, lose, or share electrons in order to acquire a full set of 8 valence electrons. In the case of sodium, it really wants to get rid of that one electron. It has a choice. It can either get 7 or lose 1. If it can lose that one electron, it'll have its full octet in the second ring, and it'll be happy. So it really wants to get rid of that 3s1. It's a lot easier for it to do that. Chlorine, on the other hand, just needs that one electron to get its octet. So it's really missing one to become and then a 2p6. If you can get one, it'll both be happy. Well, I guess you can kind of see what's going to happen here. When sodium and chlorine get together, it's a marriage made in heaven. And this is the premise of table salt. That one electron in the outermost layer of sodium is going to transfer to chlorine, so that way sodium will have a full octet and chlorine will have a full octet. And that's the premise of an ionic bond. It's a sodium and chlorine getting together. So in this case, both elements will have a full octet after they bonded with each other. Okay, the last part is pretty easy. It's called Lewis dot diagrams. Basically, it's a diagram that's used to help us show valence electrons around an atom. So since sodium has one valence electron, we're basically going to draw dots around the element to help us signify this. And so I'm just going to put one dot. And there's 4 parts to the atom, and you have to draw it. It doesn't matter for sodium which part you put it on, but there is a organization to this. So sodium has 1, you just put 1. Chlorine, on the other hand, has 7. So the way we put electrons in the correct way is we first put 1, 2, 3, 4. We want to put 1 on each side first, then we start pairing up. 5, 6, 7. So that way chlorine has a pair on 3 sides of it and a single electron on one side. And this becomes important when we into future lessons when we have to do bonding. Just to show you how to write valence electrons as dots around an element. So don't just randomly put them around the structure. It does have a little bit of order to it, rules to it. Aluminum has 3 valence electrons. So 2 plus 1 is 3. 1, 2, 3. Okay, last one. Nitrogen has a total of 5. So 3 plus 2 is 5. So 1, 2, 3, 4, and 5. It's going to have a pair of electrons and then 3 single electrons around it. And again, this becomes important later on. Okay, so let's kind of put this all together here and kind of do a couple of examples. Here we have oxygen. The outermost layer of oxygen is the 2s2, 2p4. So it's going to have 6 valence electrons. And when we draw the Lewis dot diagram, you're going to draw just a single O and put 6 dots around it. 1, 2, 3, 4, 5, 6. So that would be the electron dot diagram of oxygen. Magnesium's outermost layer is that 3s2, so it's going to have 2 valence electrons. And then since it's got 2, you're just going to put, now electrons don't like each other, so we're going to put them on opposite ends. So magnesium, there we go. Transition metals can be written with valence electrons. They're a little more trickier, but just to kind of show you, the outermost layer for iron is not the 3d6, but that 4s2. So when I want to draw a valence electron for 4s2, it's going to have 2 valence electrons. It's just going to have 2 right there because the outermost layer is a 4s2. And when I write the electron dot for iron, it's going to be Fe with 2 dots around it. Okay, bromine. It's got the outermost layer for this is a 4s2 and a 4p5 for a total of 7. So the 3d10 I'm not going to write because it's a lower level. So when I write bromine, it's just going to be Br, and with 1, 2, 3, 4, 5, 6, 7. So 3 pairs of electrons and 1 single electron. So here's a few examples of how to apply these. Now there is a shortcut to finding this information without having to do electron configuration, and it's from your periodic table. On the top of the group numbers, group 1A, right there, that means that all of these have 1 valence electrons for this entire family. The alkali metals have 1 valence electrons. Group 2A has 2 valence electrons. All of these elements will have 2. This family here, group 3A, will have 3. These will have 4. Group 5A has 5. Group 6A has 6. And you'll start to notice a trend here. Noble gases are the most stable. They will have a full octet, 8 valence electrons. So you can either draw electron configurations to find your valence electrons, or you can just simply look at your periodic table and look for the element and match it up with its group number, and you can draw the dots around there. So if I had to pick sulfur, I can see that sulfur is right there, and since it's in group 6A, I'm just going to draw 6 dots around it, and it's going to have 6 valence electrons. There you go.